Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have this lecture slides, you may refer to my GitHub page at this given link. In this lecture, we would be discussing the linear discriminant function. In parametric estimation lectures, we have been discussed that how we can estimate the parameters of the probability densities of known form using training samples, and the estimated parameters of the probability densities are used to define the discriminant functions that help to make decision easier. However, in this lecture, we assume that we know the proper form of the discriminant functions instead of assuming the known form of probability densities, where a set of training sample is used to estimate the values of parameters of discriminant functions that constitute the classifier. Therefore, we can say that this is a kind of non-parametric approach. This approach of linear discriminant function is relatively easy to compute and estimate the form of linear discriminant functions using training samples. Under linear discriminant functions, we would be covering discriminant functions that are either linear in the components of sample X or linear in some given set of functions. Let us talk about discriminant functions that are linear combination of component of sample X. So it can be written as Gx equal to W transpose X plus W0, where W is the weight vector and W0 is bias or threshold weight. And if we put Gx equal to 0, then it defines the decision surface that separates the points associated with different class. In this lecture series, we would be covering linear discriminant functions for two category case, multi-category case and general case. However, in this lecture, I would be covering the linear discriminant function for two category case and multi-category case, and the general case will be covered in the next lecture. Now, let us discuss the two category case. A two category classifier with discriminant function of the form Gx equal to W transpose X plus W0 can be defined as if the discriminant function is greater than 0, then sample X will be classified to class omega 1, otherwise omega 2. That means Gx equal to W transpose X plus omega 0 is greater than 0, then we have to decide class omega 1. So we can write W transpose X is greater than minus omega 0, then we have to decide omega 1. So we can say that X is assigned to omega 1 if the inner product W transpose X exceed the threshold minus omega 0, otherwise it will be classified to omega 2. So we can write the two category classifier as decide omega 1 if the inner product W transpose X is greater than minus omega 0, otherwise omega 2. but these decision rules does not define the data points on the decision boundary. And if so if Gx equal to 0, that means the x sample is on the decision boundary, so x can ordinarily be assigned to either class or can be left undefined. In this lecture, we will left undefined this data sample x, which is on the decision boundary. Here this figure shows a simple linear classifier where the input is x1, x2 and xd. So these are the basically the components of feature vector. So if x is a feature vector, then x1, x2 and xd are the feature components of d-dimensional feature vector, and x0 equal to 1 is the input to the bias. Then the weighted sum of these inputs, that means the x0 will be multiplied with w0, x1 will be multiplied with w1, x2 will be multiplied with w2 and xd will be multiplied with wd. So the weighted sum will be collected at this point. So we will have Gx equal to x0 w0 x1 w1 plus x2 w2 and xd wd. So this is the weighted sum, and if we put the value of x0 as 1, so it will be w0 plus it is summation of x I wi, where I equal to 1 to d, or we can write this is the basically the inner product. Okay, so we can write the final term as w0 plus w transpose x. So this is nothing but our linear discriminant function. Okay, so at this point we are getting the linear discriminant function, but this Gx is passed through a threshold function. Okay, so let us assume that fx is our threshold function, so we can write, okay, and this is the final output. So it will be plus 1 if Gx is greater than 0, and it will be minus 1 if Gx is less than 0. Okay, so this is called threshold function. Okay, so here each input feature vector xi is multiplied by its corresponding weight wi, and the output unit sums all these products and emits plus 1 if w transpose x is greater than 0, which is basically the discriminant function, and it will be minus 1 otherwise. Okay, now try to analyze the linear discriminant functions and its parameter with respect to the feature space. Okay, and we will also try to observe that how this discriminant function is related with the distance measure in the feature space. Okay. So, before that we will look at a few points which is very important to understand the other things. Okay. We know that Gx equal to 0 and it defines basically the decision surface, and this decision surface, it separates the points assigned to class 1 from the points assigned to the class 2. That means whatever the point we have in the class 1 and whatever the points we have in the class 2, that will be separated by this decision surface. Okay. And if Gx is linear, then we will have the decision surface that is called the hyperplane. Okay. And let us consider we have the two random points x1 and x2 on the decision surface. Okay. So, these 2 points can be anywhere on the surface. So, we know that decision surface is nothing but the Gx equal to 0. So, if we have the 2 points x1 and x2, so we can write Gx1 equal to 0 and Gx2 equal to 0. So, we can write Gx1 equal to Gx2. Okay, it is very easy. So, this Gx1 we can write W transpose x1 plus W0. Okay. So, we can write like this. Okay. Similarly, we can write Gx2 as W transpose x2 W0. Okay. So, just cancel this omega 0 from the both side and we will take the common W transpose and then we will have this expression. Okay. So, this x1 minus x2 is nothing but a vector which joins these 2 points. So, x1 minus x1 minus x2 is a vector which joins these 2 data points in this surface. Okay. And the dot product, that means inner product of this vector with W transpose is equal to 0. That means this vector which joins the point x1 and x2 is perpendicular to the weight vector W. Okay. So, which shows that the W is normal to any vector lying in the hyperplane, because x1 x2 is basically any random point on this surface. So, if we take any 2 points on this surface, then that the vector joining these 2 points will be perpendicular to the normal vector. So, the normal vector is perpendicular to any 2 points on this surface. Okay. Now, try to understand that how the discriminant function is related with the distance measure. So, here we can see that the discriminant function Gx gives an algebraic measure of distance from x to the hyperplane. Okay. So, look at this 3-dimensional feature space and x is our feature vector and here xp is the normal projection of x on this decision surface at the distance of r. Okay. Then we can write this vector as r into the unit vector in this direction, some unit vector in this direction, and this unit vector is nothing but basically the vector. This is the normal to the surface, and normal to the surface we have which vector? We have the W vector. So, but we have to make it normal vector. So, we can write r W divided by the norm of W. Okay. So, this is the basically the vector, and xp is basically the point vector. So, it will be from origin. Okay. So, this is another vector, and we can denote x as the algebraic sum of these 2 vector. Okay. So, we can write x equal to xp plus r into W by norm W. Okay. So, here the desired algebraic distance, which is positive if x is on the positive side and negative if x is on the negative side. That means, this r will be negative if the g x will be less than 0. That means, that will be the negative side, that is the basically R2 region where g x is less than 0. Okay. So, if r will be negative, if r will be positive, then this will be the positive side. Okay. And we can derive that this r is nothing but the r equal to g x divided by the norm of w. So, we can prove it. So, g x equal to w transpose x plus w 0, and what is x? X is nothing but the x p plus r w divided by w norm. Okay. And plus w 0. So, we can write w transpose x p plus r w transpose w divided by w norm plus omega 0, and w transpose x p plus w 0 plus r w transpose w divided by norm. Okay. And this term is basically the discriminant function on the boundary, which will be 0. So, we can write g x equal to r, and so this is the inner product. So, w transpose w, we can write it as norm square. Okay. So, we have this value, or we can write r equal to, or we can write r equal to g x divided by w norm. Okay. So, here this r is nothing but the algebraic distance, which is positive if g x is positive and r is negative if g x is negative. That means, the discriminant function g x is proportional to the signed distance from x to the hyperplane with g x is greater than 0 when x is on the positive side and g x is less than 0 when x is on the negative side. Okay. The next observation is that the distance from the origin to h, that means, what is the distance of the hyperplane from the origin? So, we know that if we have a hyperplane, which is, if we have hyperplane which is w transpose x plus w 0 equal to 0, then the distance from the origin will be given as we will put here x equal to 0. So, it will be w 0 divided by norm of w. Okay. So, it is w 0 divided by the norm of w, and if w 0 is positive, the origin is on the positive side of the h. So, when the w 0 is positive, then the origin is on the positive side of h, and if w 0 is negative, it is on the negative side. Okay. Then the origin will be on the negative side. Okay. So, if you will look at here, for this case, this origin is basically on the negative side. If we assume that this gx is less than 0 for R2, then definitely this omega 0 will be negative. Okay. And if omega 0 equal to 0, then gx has the homogeneous form w transpose x and the hyperplane passes through the origin. That means we have the discriminant function w transpose x plus w 0. That means this is our discriminant function. Okay. And if this omega 0 will be 0, then gx equal to w transpose x, and this is basically the homogeneous form, and this hyperplane will pass through the origin. Okay. So, in conclusion, a linear discriminant function divides the feature space by hyperplane decision surface. Okay. And the orientation of the decision surface is determined by the normal vector w, and the location of the surface will be determined by the term bias. Okay. And also the discriminant function gx is proportional to the signed distance from x to the hyperplane, with gx greater than 0 when x is on the positive side and gx is less than 0 when x is on the negative side. Okay. That means if r is greater than 0, means this is on the positive side. That means this is for gx is greater than, that means gx is greater than 0, and if r is less than 0, then that means gx is less than 0, because what we derived? We derived that r is basically the gx divided by norm of w. So, it is basically the signed distance. So, if r is positive, gx will be positive, if r is negative, gx will be negative. Okay. Now, let us discuss multi-category case. There is more than one way to design multi-category classifier using the linear discriminant functions. So, here I have shown the two examples. So, in the first example, suppose we have to classify the C category problem. Okay. Then for that we can design a problem using the C2 class problem. Okay. That means we will consider 1 versus rest. In this figure, we have 4 categories: omega 1, omega 2, omega 3 and omega 4. So, if we apply the C2 class problem, that means 1 versus rest, that means for the first 2 class problem, omega 1 will be our the first class, and the rest of the data samples belongs to the different class will be the sample which is not belong to omega 1. Okay. That means it belongs to omega 1 and not belongs to omega 1. Okay. Similarly, we can define the another 2 class problem where the omega 2 will be the number the samples, and the other class will be the which is not omega 2. Okay. So, similarly we can have this decision boundary, similarly we can have this decision boundary. So, a C class problem can be devised using C2 class problems. Okay. So, this is the one approach, and which is called the 1 versus rest. In another approach, we will make the combination of the pair of the class. Okay. So, suppose we have 4 class problem, then we will make the pair, that means we will find the combination of the 2 class. So, it will be 4 into 3 divided by 2. Okay. So, that means it is basically C into C minus 1 divided by 2. So, these are the number of linear discriminant function that we can design to solve this problem. So, in this case it will be 1 for every pair of classes. So, we will define the discriminant functions we will define the discriminant function for every pair of the classes. So if we have the 4 class, that means how many pair of classes we will have? We will have 4 C2, and that is basically C into C minus 1 divided by 2. So in this way also we can define our multi-category classifier using linear discriminant functions. However, both of these approaches can lead to ambiguous region where the classification is not defined, like this pink region, where if the sample will fall, then it is difficult to make the decision whether it will belongs to class 1 or 2 or 3 or 4. We can avoid this ambiguous region by considering a linear discriminant function for each C class. That means there is another approach, that if we consider the linear discriminant function for each individual class, then this ambiguous problem can be overcome. So for that, let us consider a linear discriminant function for ith class. As so GIX equal to WI transpose X plus omega I 0, where I equal to 1 to C. That means for all the classes we have the discriminant function, and we assign X to omega I if GIX is greater than GJX for all value of j not equal to I. Okay. So in this case, the resulting classifier will be known as the linear meshing. In this case, resulting classifier is known as linear meshing. Okay. Therefore, the linear meshing divides the feature space into C decision regions. Okay. So how it will define? So the linear meshing divides the feature space into C decision regions. Okay, and those regions are basically R1, R2 and RC. So these are the basically regions. The feature space is divided into C regions with GIX being the largest discriminant if X is in the region Ri. Okay. That means GIX will be the largest discriminant value if X is in the ith region for two contiguous region Ri and Rj. That means, if these two regions are side by side, then definitely our decision boundary will be Gix equal to Gjx. Okay. So, this will be our decision boundary. So, what we can write, Gix equal to Gjx. So, we can write in terms of linear function okay, and then Wi Wj transpose x plus Wi 0 minus Wj 0 equal to 0. So, it shows that the difference between these two vector is normal to the surface between these two regions. Okay. Wi, so it shows that Wi minus Wj is normal to the surface Hij, that means the surface between the region Ri and Rj, and this is nothing but the separating plane between class I and J. Okay. So, the algebraic distance. So, how we can write the algebraic distance in this case? So, the algebraic distance from x to the separating plane is, so R equal to Gix minus Gjx. Okay. So, we can write in this way, and the Wi minus Wj norm. Okay. So, as we have seen in the earlier case. So, now look at this the decision boundary using this type of multi-category classifier. Okay. So, in this case we will have the decision boundary which separates the points belongs to different class, and here we do not have any ambiguous region. So, it is clear here that this approach does not leave any ambiguous region in feature space. So, if you have any doubt, you can ask in the comment section. Thank you.